Alright, in this video we're going to revisit the Ekman spiral equations, but we're going to solve them numerically, and we're going to solve them using a method called finite differences. And that means we're going to convert the derivatives in the equation into finite differences, which will make them linear algebraic equations instead of differential equations. And then we're going to use the computer to solve these algebraic equations. So what we're going to do, if you remember the equations for the Ekman balance was the Coriolis force per unit volume minus rho naught F times U. And I'm going to drop a little E here just for keep the notation neater. This is the Coriolis per unit volume in the, this is a V, in the X momentum equation is equal to the convergence, so that's minus the divergence of the diffusive flux of momentum, which is down gradient, so minus rho AV du dz. So this quantity over here, that's the stress, tau. This is the vertical component of the divergence, and we want the convergence, so we put a negative. So these two negatives made a positive before, but I think this makes the physics a little bit more clear in this case. All right, so that's the X momentum equation, and the Y one is a plus rho naught, this marker's dying, plus rho naught F times U is equal to minus d by dz minus rho AV dv dz. Right, so this is the northward momentum flux. This is also tau. I guess tau, this is tau in the y direction, this is tau in the x direction for stress. Remember, stress is a force per unit area, or the flux of momentum. In this case, upward flux of eastward momentum, upward flux of northward momentum. All right, these are the equations we solved before, and this time, to solve it numerically, we're going to go back to the time-dependent form. So remember, we solved the steady-state equations before, and we neglect the time derivatives. Now we're going to bring those back from the dead. So this equation, there was a du dt here, and in this one there's a dv dt. So we will retain these time derivative terms. We're not going to keep the nonlinear terms, we're going to leave them out, assuming that they're small, but we will retain the time dependence, and we're going to solve the time dependent problem instead, which I think is going to be more illustrative, and in some ways it makes the problem a little bit easier to solve than solving directly for the steady state. All right, so what kind of equations are these? So now we have two independent variables. So the first point is two independent variables. T and Z, and we have two dependent variables, U and V. And so this time, these equations, because there's now T derivatives and Z derivatives, these are partial differential equations. So this is two coupled partial differential equations. And so the goal is to find, U as a function of Z in time, and V as a function of Z and T. So now we're looking for multi-value functions, not multi-value functions, we're looking for functions that are of multiple arguments, so of Z and T. And we're going to, like I said, we're going to replace these derivatives, both the time derivatives and the space derivatives, using finite differences. So the first thing I'm going to do is I'm going to convert this derivative, this d dz, into finite differences, and this d dz into finite differences. So let's I'll show you a little bit how we're going to do that before we go to the computer. Okay. Let me move. Oh, I'm going to erase the whole thing. All right, so the mesh, we're going to have the sea surface, and we're going to define the stress at the sea surface, tau wind, and this will be applied. This will be an applied wind stress, so we don't have to solve for it. This is prescribed by the wind. Then, at depth below that, we'll define the first or the last velocity, I guess. V, and we're gonna order them in increasing z direction. So the first v is going to be deep in the ocean. I'll call it v0, and that one will just be equal to 0. Deep down enough. We saw that the Ekman spiral decays to 0. So down here, we're going to impose velocity 0. Then we're going to have the stress, tau 1. Then we're going to have the velocity again, v1. So this is a variable we're going to have to solve for. And then we're going to have the stress again, tau 2. And then the velocity again, v2. And the stress, tau 3. The velocity, v3. And the stress, tau 4. And then v4. I guess I'm going to keep 5 points to make everything look, to make everything clear. v4, tau 5. We're still in the ocean. And then v5. And then finally the sea surface. Up here. Tau 6 or tau wind. So this one here is not going to be solved for. This one is known. So this one is identically 0. So we don't solve it for it. So the variables on our finite mesh, this is z. And this is z equals 0. And over here, write it nicer. This would be z is equal to minus delta z. Z is equal to minus 2 delta z. Z is equal to minus 3 delta z. Z is equal to minus 4 delta z. And z is equal to minus 5 delta z. And the v points, well, this last one here, which we're not going to solve for, that would be at a delta z by 2 deeper down. So this would be z is equal to minus 5 delta z minus delta z over 2. And this point here would be halfway between these two. So this point is going to be at z is equal to minus 4.5 delta z. Z is equal to minus 3.5 delta z. Z is equal to minus 2.5 delta z. Z is equal to minus 1.5 delta z. And z is equal to minus 0.5 delta z. So the velocity point, so it's a staggered mesh where the velocity points at all the half marks down the water column, and the stress points where we impose the momentum fluxes are going to be at all the integer valued multiples of delta z. And so the system of variables we're going to solve is going to be for 1, 2, 3, 4, 5 stresses and 5 velocities. And we're going to impose the fact that the velocity is 0 down here and the fact that the wind stress is known up here. So that's why I'm going to have to create 2 d by dz differential operators. One of them is going to represent the gradient. So if I want to compute the stress tau 5, for example, I'm going to take what I would like is dv dz and then multiply by the constants. And so to compute dv dz, I'm going to do it as a finite difference as v5 minus v4 divided by delta z. So let me explain that more clearly here. So we're going to start at the bottom here, and suppose we want to compute tau 1. So tau 1 is going to be set to minus rho naught AV, and then I would like to have well, let's do the x component, du dz, right? I want du dz. And since we're going to replace this du dz using a finite difference, so remember the definition of the derivative, du dz is equal to the limit as h, or maybe I could put delta z in this case, delta z goes to 0 of u at z plus delta z minus u at z, right? And then divided by delta z. So this is the definition of the derivative. We take the limit as delta z goes to 0 and we get the derivative. And here we're going to do a finite difference. That means we're going to avoid doing the limit. So that's kind of nice. When you took calculus, you learned how to take all these limits to go from this to that, and then we manipulated these derivatives around. Now we're going back in the opposite direction. We're going back to the finite differences. So we're going to approximate this du dz by this expression. So for example, if I want to compute tau 1, like I was saying, I'm going to replace this du dz by u2 minus u1 divided by delta z. And that will be my, sorry, it'll be, let me correct myself, u1 minus u0. So this will be u1 minus u0 divided by delta z. Remember, u0 is defined out here, and I guess it's also 0. u0 equals 0. So in fact, this one is 0, so I can just leave it out. So this will just be minus u1 over delta z in this case. So here I've used the boundary condition. So I've already built in this fact that below tau 1, the velocity has already vanished. All right, let's compute tau 2 over here. So tau 2x is going to be minus rho AV. And then I want to take v2 minus v1 divided by delta z. So v2 minus, or u2 minus u1 divided by delta z. And then tau x3 is minus rho naught AV. u3 minus u2 divided by delta z. Tau x4 is minus rho naught AV. u4 minus u3 divided by delta z. Tau 5x, the last one, is minus rho naught AV. u5 minus u4 divided by delta z. And then the surface wind is prescribed. So these finite differences here are the ones I'm going to use to define what I will call the gradient. So right, the diffusive flux of momentum is parameterized as being down gradient, so from regions of high momentum to low momentum. And so we need to compute a gradient, and we're going to use a finite difference version of the gradient. All right, so this is going to be, in this example, my 5 momentum fluxes are going to be defined as follows. And on the other side, I'm going to do, and I guess if I wanted the y component of the stress, I would just replace the u's by the v's. So it would be almost the same. If this was the northward component of the stress, this would be v1, v2, v1, v3, v2, and so on. Now I'm going to do for the stresses. So I'm going to erase all this so that I have space to put the stress on the other side. So for the stresses, what we are going to use, the way the stresses will show up in the equation is to compute the acceleration of v1. And so that means we will have to compute the convergence of the stress over the momentum, the convergence of the momentum at the point v1, and that convergence is going to give us the acceleration of v1. So if there's a convergence of momentum, the flow will accelerate. So we're going to need to do what's called the negative of the divergence to get the convergence. And to get it at the point v1, we're going to do tau 2 minus tau 1 and divide by delta z. So the divergence, so here the acceleration, I just call it div1, or minus, just div1, that is going to be tau 2 minus tau 1 divided by delta z. Right, because tau 2 is the flux out, and this is flux in. So it's a divergence because the tau 2 is positive upward. So tau 2 is momentum flux out of the layer with v1, and tau 1 is into the domain, but we put a negative, so it's both flowing out. So this is the divergence. This is kind of like how much momentum is leaving this layer. And to get divergence for layer 2, that will be tau 3 minus tau 2. Divergence for layer 3 will be tau 4 minus tau 3 divided by delta z. I forgot the delta z. And then for tau 5, the divergence here, or sorry, for d4, the divergence will be tau 5 minus tau 4 divided by delta z. And over here, for divergence for velocity at level 5 will be, so remember tau wind is into the domain, so this one has the opposite sign of the other ones. So I'm going to put minus tau wind, because now that is the upward component of the wind stress, so it's sort of the stress of the ocean on the atmosphere, so it's the flux into the atmosphere, minus tau 5 over delta z. And this one is known, so I'm going to use the boundary condition that we know tau wind to compute this one. And on the bottom, we don't need to use the boundary condition. So if you notice, when we did the velocities, we used the boundary condition at the bottom to compute the stresses. And now to do the divergence, we use the boundary condition at the top. So the divergence and the gradient are related to each other. In fact, they're just, the finite difference ones can be expressed as matrices, and they're just transposes of each other. And we're going to set those up right now. So if I can erase the middle part and these divergences, I'm going to convert this gradient into a matrix operator. So let me erase all this. So we have space. So the gradient, in this case, gradient is going to be times the velocity vector, u. I guess I'll write it as an explicit vector here. u1, u2, u3, u4, u5. So this is the bottom of the ocean, and this is the surface of the ocean. So it's counterintuitive that increasing indices are going upwards, but in vector notation we put them going downward. This causes endless confusion for me, but that's the way I'm going to set up. Actually, I'm going to shift over everything so I have more space. Grad times u1, u2, u3, u4, u5. And that's going to be 1 over delta z. Right, there's a delta z everywhere in the denominator, and now I'm going to put in the expressions. So to get the first tau 1, what I want is just a u1 over here. So minus u1. Sorry, to get the gradient is just u1, and then we do minus the gradient to get tau 1. So the gradient, this would just be a 1 over here, and then 0 is for the other 2, 3, 4, and then u1, u2, u3, u4, u5. So built into this first row of this gradient operator is the fact that the velocity goes to 0 at layer 0. So there should be a minus u0 over here, but I don't store the u0. It's implicitly built in here that it is 0. And now to get the gradient at the tau 2 point, stress points, I have u2 minus u1. So that's going to be a minus 1 and a 1, 0, 0, 0. To get the next one will be 0, minus 1, 1, 0, 0, right? This is 0 times u1 minus u2 plus u3, plus u3 minus u2. The next one, 0, 0, minus 1, 1, 0. And the last one, 0, 0, 0, minus 1, 1. So this expression here, this is the gradient operator. Infinite differences in one dimension. Okay, now we want to do the divergence. The one we had over here, I wrote it and I erased it, but I'll put it back now. So on this side, we're going to do the divergence. maybe I'll just write this on top. So grad of u vector is equal to this. And I can erase and give myself more space. Alright, so divergence div of u, and that's the little underbar, oh, not divergence of u, of tau x. The little underbar means that's a discrete vector of values for them at the mesh points. Alright, so let's do the same thing. It'll be 1 over delta z. And then I multiply by the stresses. Tau 1 x, tau 2 x, tau 3 x, tau 4 x, tau 5 x, and then the last one is tau wind with a minus in the x direction. Alright, so to get the divergence of the stresses or the momentum fluxes onto layer 1, what I will use is tau 1 and tau 2, right? Remember the u1 was staggered between the tau 1 and tau 2 stresses. So this will be minus 1, 1, 0, 0, 0. And then for layer 2, I guess I have 6, 1, 2, 3, 4, 5, 6. I have 6 points. So I suppose I should add one more, 0. Where the 6th one is for the wind. Alright, and then for layer 2 will be 0, minus 1, 1, 0, 0, 0. So this will give me minus tau 2 plus tau 3, or tau 3 minus tau 2. And then 0, 0, minus 1, 1, 0, 0. That's tau 1, u1, u2, u3, u4, 0, 0, 0, minus 1, 1, 0, 0, 0, 0, 0, minus 1, 1. And I guess that's 1, 2, 3, 4, 5. Yeah, that's good. 5. So this expression, this here is the div operator. From here to here, this is the div matrix. And this one is a rectangular matrix because I'm going to build in the wind stress to add an extra row. So I'm going to build in the boundary condition like that. So this matrix here, divergence has 1, 2, 3, 4, 5 rows. So it's going to give me 5 outputs, namely the divergence for each of these velocity points. And it has 6 columns because there are 6 wind stresses. 6 stresses, one of which is the wind stress at the surface. Alright, and notice how here it's going to be minus tau 5 minus tau wind, right? So I built in the correct sign that the stresses are assumed to be positive upwards. Okay, so that takes care of how we're going to do the finite differencing to do the z derivatives. We're going to build a div operator and a grad operator, and we're going to be able to compute the time tendencies, or the rate of change in time of the velocities u and v. So now I have to tell you how we will do the discretization for the time dependence. And for that, we're going to do the following. Given u and v, I will compute the stresses. So at time t. Sorry. So given this, we're going to compute tau vector, tau x, and tau y, and that's going to be equal to minus rho naught AV, and then we'll have gradient grad of u, and followed by the wind stress, tau x wind, and then grad of v, and then minus tau y wind. So this part here, this vector here, this is the matrix times u, and with one extra element, which is the negative of the wind stress, is going to give me tau, the eastward component of the stress, and gradient of V minus tau wind multiplied by this prefactor will be tau y wind. And then we'll get U and V at time t plus dt is going to be equal to U and V at times t plus delta t, right? So it should be, the derivative should have been this minus this divided by delta t equals to the right hand side. I brought the delta t over, and now we're going to write it down like this: divergence of tau x, divergence of tau y, with a minus because we want the convergence. And we also need the Coriolis forces, so plus F times V and minus F times U, like that. And that allows us to, if we know U and V at times t, everything here, this is also at times t, So we can now use this to find U and V at times t plus delta t. Then we can come back up here and solve for the stresses at the new time step, and then take the divergence or the convergence with the negative plus the Coriolis force and get the updated U and V. And we can march through time that way and compute the velocity fields at every time step until we stop it or until we reach a steady state. I think from here on it's easier to go look at the computer at the actual code. All right, so let's go and do that. Okay, so let's do the numerical solution to the Ekman spiral. So we'll do it in MATLAB. So I'm going to start MATLAB in this window. And over here I have my text editor open in a file called ekman.m. And let's start the code. So the first thing we'll do is create a mesh of points and of z points, and then we're going to plot the solution, the analytical solution first. So let's create, make a mesh of discrete z points. So I'm going to define dz, excuse me, to be, let's say, 10 meters. And then z is going to be from minus 200 in steps of dz all the way up to 0. So this is the height coordinates. This is also in meters. And then we're going to define the analytical solution. So first there were two parameters. First is AV, A sub V, and I'm going to pick that to be 10 to the minus 3. Minus 3. And that's in units of meters squared per second. And then we have the Coriolis parameter, F. We're going to pick that one to be 1 e to the minus 4. And that has units of inverse seconds. Just 1 over seconds. And then I can define that delta variable. So delta is equal to the square root of AV divided by F. And this also has units of meters. Then I can define the solution. So UE is equal to, I didn't specify tau x. So tau x is equal to 0.0 or 0.1, and that would be in newtons per meter squared. And tau y, I just chose it to be 0. But if it did have units, it would also be in newtons per meter squared. And this is the eastward component. And this is a northward component. Now the solution. Okay, so now, oops, define the analytical solution. UE is equal to a function of z, and it's tau x times, I guess it's delta, times tau x divided by rho naught times AV. And I guess I need to define rho naught. And this should be a capital AV, so rho naught 1000, and that is in kilograms per cubic meter. That's the density of seawater, or reference density. I could make it a little bit bigger, I guess, 125 maybe, make it a little bit more accurate, because seawater is salty. Alright, so that times star exponential minus z star square root of 2 divided by 2 star delta star cosine of, maybe I should define a better length scale. This is annoying, right? So when this is delta, I'm going to define d. d is equal to delta times square root of 2 divided by 2, I think. Like that. That'll make the solution a bit nicer. So exponential z divided by d times cosine of minus z divided by d plus pi by 4. And then VE is equal to c delta times tau x slash rho 0 star AV star exponential z slash d star sine minus z over d plus pi by 4, and there should be a minus out here, and then this one is a plus, just to line up my equations, and then another thing to do is since, well, the first term here is a constant, but this one I can pass in, if I pass in a vector of z, then this will evaluate to a vector of values, and then I want to multiply element wise, so I should put a dot here for this multiplication and a dot here. Alright, and let's see if we can make a plot. So plot UE comma z comma line width 2 red, and then hold on and plot VE comma z line width 2 in blue, and then set GCA font size 16 so that you can see it. This will just make the plot easier to see, and I guess I should put some labels. So X label is UEVE in meters per second. Y label is just Z in meters. Let's try it. Okay, so let's run an Ekman. Invalid arguments. Oh,
Yeah, I have to define what UE is, right? So I have to call UE and evaluate it at the z points. So these two lines over here, they define U, E, and V as functions, and then I have to evaluate them at the z points that I defined on the mesh. So let's try again. Ekman data must be a single. Let's see, UE of z, VE of z, z, plot UE of z comma z. That seems to work. Why didn't it plot? Okay, so let's put more grid points. I'll start at DZ is 1, and it looks like my value of AV makes the Eppin layer decay very quickly. So we don't need to go down to 200 meters, we can just go down to 60 meters. Let's try again. Alright, so that's looking nicer. Maybe we can make our vertical diffusivity a little bit bigger so that the Ekman layer is thicker. So let's make it even -1. Clear all Ekman. Oops, see that was too drastic. Be -2. Ekman. Right, that looks nice. Let's add a grid. Grid on. And again. Okay, and then in figure 2, figure 1, and then figure 2, let's plot the spiral. So figure 2, quiver 0 times z, 0 times z. I don't know if this works. UE of z, VE of z. Let's try that. Right, that looks good. And let's set GCA font size 16. Grid on X label X meters per second. I guess that's not X, that's U Ekman. And Y label VE in meters per second. And then set GCA font size 16, grid on, clear all Ekman. Okay, so this one shows the U velocity. I think U is in blue. What should I pick? No, U is in red, so this is the U velocity. And this is the V velocity as a function of depth. And this is what they look like. This is the spiral. So that's the vector at the surface where the current is fastest. And as you go down with depth, the speed is getting slower and slower, but it's also the velocity vector is also changing direction and it's spiraling downwards. Alright, so that's our analytical solution. So much for that. Let's now try to find the numerical solution using the methods that I described in the video lecture.
we're going to now compute the numerical solution, and we're going to implement these finite difference schemes that I talked about in the previous lecture. Okay, so we're going to work in this window. This is my Emacs screen over here, and this one is my MATLAB screen. Let me make the font a little bit bigger. Control X plus. Okay, hopefully you can see. So this is going to be the spin up of the Ekman spiral. Alright, so what do we need? First we'll start off by defining the parameters. What did we use last time? Yes, so we're going to copy these parameters. Okay. So this is the kinematic viscosity, or the momentum diffusivity. This is the Coriolis parameter. This, I don't need this delta anymore. I'm going to do everything dimensionally this time. Get rid of the D. Well, actually, maybe I will keep these. These could be useful because I can use that to make sure I have enough grid points. Because D is going to give me the kind of thickness of the Ekman layer, and I can make sure I have enough grid points to resolve the Ekman layer. Alright, these are the stresses for the wind at the surface. Maybe I'll put an underscore W for wind, underscore W for wind. Alright, then we want to define a mesh. So define the staggered mesh. Oops. Define the mesh for the tau points. In other words, the points at which we define the stresses. Z is equal to Lin space. We're going to go from the bottom, which will be minus maybe 6 times D, so 6 of these Ekman layer depths kind of things, all the way up to 0. And we're going to pick, let's say, 5 mesh points. And then dz will be z2 minus z1. Alright, let's run it and see what we have. ek, and then dz. So dz is 21, z, these are my z values. So the bottom, the deepest point is at minus 84 meters, minus 63, minus 42, minus 21, and then the surface is at 0. Alright, that looks good. 2, 3, 4. I guess we need an extra point, 6. Because I want to have 5 stress points, and here I have only 4 because the first one is the wind one. So I should get 6 if I include the wind point. Alright, so let's try it again. Ekman Z. Yeah, that's better. Okay, so I will define here n is equal to 5. So we can increase it later, and this is n plus 1. Alright, so then we can define the mesh of U and V points, and those will be staggered starting at delta Z above the last stress point. So these are going to be, I guess I'll give these a different names to remind me those are the stress points. So I'll call them Z S for stress, ZS, ZS, and then for the velocities I'm going to use Z velocities. Alright, so then we're going to start at the very deepest, I guess they're going to be the same as the stress point, ZS, but we're going to shift them all up by delta Z by 2. So they're all half a grid point above the stress point. So ZS, but we want to exclude the very top one, the 0 one, because the half a grid point above that would be in the atmosphere. So that'll be 1 through n minus 1 plus dz divided by 2. Alright, let's run it and see what we get. Heck. So now the z stresses, like before, and the z v points, like this. Yeah, that's good. So notice that the stress points there's 6 of them, including the surface where we prescribe the wind, and there's 1, 2, 3, 4, 5 points where we'll define the velocities. Alright, the next step is to define
define the gradient operator, div and grad, I guess, div and grad. Alright, so there's different ways of doing this. One way is by permuting the elements of a identity matrix to shift the values we want, or the other one is to explicitly construct the matrix by populating a matrix with the diagonals of 1s and minus 1s. And we're going to do the latter method. We're going to construct the matrix. So to avoid having to store all the zeros, which is not too bad if we have a small system with only a few unknowns, but when we go to higher resolution, when n becomes in the hundreds, then these differential operators are going to be very big with lots of zeros, and we don't want to have to store all these zeros, so we're going to use sparse matrices. So the gradient operator, we're going to write it as 1 over dz times, and then we're going to use a function called sparse diags, or spdiags. That's a MATLAB function to create sparse matrices by populating the diagonal elements. So you can do help spdiags. You can find out more about it. And the way it works is you specify the diagonal. So this would be diagonals, what you want to put on them. So in this case, they put a 1, a minus 2, and a 1. And then the minus 1 to 1 here, these are specify which diagonals we're going to populate these columns with. In other words, the minus 1 diagonal, so the way it's indexed is the main diagonal is called diagonal 0. Every diagonal above that, or diagonal 1, 2, 3, 4, 5, and so on, and the ones below the main diagonal are minus 1, minus 2, minus 3. So for our case, we're gonna follow this example and create an e of 1s just like they do. So let me do that. E is equal to 1s, n comma 1. Maybe n, yeah, I think that's right. And now we're going to have minus e and minus 1 and 0. And this matrix will have, remember it had n by n, 5 by 5, right? The gradient one? I think that's right. So let's try it out. Clear all, ec, grad. So grad is, see, it only stores the non-zero elements. If I do full of grad, then it'll fill up all the zeros, and we can look at the expression. So this is the first one, where the minus one here, that would be reaching to u or v0, which is assumed to be 0, and so we don't need to store that one, so we can reach out and get it. We don't need to put the minus 1. It's outside of the domain, where the velocities are assumed to have already vanished. Alright, so that's the gradient operator. Then we can define the div operator. So div is equal to 1 over dz star spdiags minus e comma e. And this time we need an extra point, right? We want 6 columns. So I guess I have to define a new e1s, n plus 1 to 1. And then we go from minus 1 to 1. And this time it will be an n plus 1 comma 1 comma n, sorry, matrix. No, the other way around. N plus 1 comma n. So we have n plus 1 columns because we will have n plus 1 stresses. We'll have 6 stresses because we're going to include the wind stress in the vector that the divergence operates on. Alright, so let's look at what we get. Clear all. So full divergence. Oh, not minus 1, 1, minus 1, 0. Right, see how here the main diagonal is all zeros? That's because I made a mistake. I populated my minus 1 and my vectors of minus 1 and 1 on the minus 1 and 1 diagonal instead of the minus 1 and 0 diagonals. So let me try again. Clear all, full divergence. Yeah, that looks better. No, that's still not right. See, we're offset. I have 0 over here. What I want is it starting at the other end. So I guess I will do it like this. 0 and 1. And 1. So I'm going to populate on the main diagonal and one diagonal above. Alright, Ekman full divergence. Yeah, that looks good. So even though these are both d by dz's, because of the way we apply the boundary conditions at the bottom and at the top, they end up being slightly different operators. This one you could think of it as a backward difference, and this one as a forward difference. So they are different discrete representations of the z derivatives, but they're a little bit more physical in the sense that it goes back to the fundamental physics that we have a gradient and a divergence, and they're not exactly the same. Even though they're both z derivatives, they're not the same operators. Alright, so that's good. So now we have our discrete operators. We're ready to write the loop in which we time step. We march through for the solution. So first I'm going to define an initial condition for u and v. And that's going to be simple. I'm just going to say u is equal to zeros n comma 1 and v is equal to zeros n comma 1. So we're going to start from a state of rest. Alright, these are the initial conditions, and then we're going to define the time step size, delta t. So define the time step size, dt, and I'm going to pick it to be, let's say 1 minute. I don't know what's the right value to pick. 60 seconds. And t starts at t equals 0, so this is at t equals 0. And let's say we run the model for, let's say at first just 2 days. So I'm going to do while t is less than 2 days in seconds, which is 24 times 60 times 60, and then 2 days multiplied by 2. Maybe I could put a big T to find the length of the run. 2 times 24 hours times 60 squared, length of run in seconds. So while t is less than t, I'm going to do some stuff, and each time I go through I'm going to update the time. T is equal to the old t plus dt, and then I'm going to also have to update the velocities each time I go through the loop. So this will keep executing this block of code until t becomes bigger than the big T. Alright, so define u, not u, the tau. So tau x is equal to minus rho 0 star av star grad star u, like that. And then we want to concatenate to that the wind stress. So semicolon minus tau x wind, I think. Is that what I called it? Tau x, oh, w. Alright, so this tau x here is going to be 1 longer than the u point. So the gradient is going to return 5 taus, and then we're going to add at the surface, which is the last point, the wind stress. And then we can do the same thing for the y stress, minus rho 0 star av star grad star v, and minus tau x, tau y, w. Did I define tau y? Yeah, just 0. Alright. And then I can update u and v. So I oops, not caps, du, come on, du dt is equal to minus the divergence of tau x plus f times v, right? Yes. And then dv dt is minus the divergence of tau y minus f times u. And then I could update u and v by saying u is equal to the old u plus dt times du dt. And v is equal to the old v plus dt times dv dt. And now, at each time step, I suppose I could plot the solution. Why not? Let's plot the solution. So I'm going to do a quiver plot. So quiver 0 times z, 0 times z. So this is really the u and v, the northward and, sorry, this is where I'm going to plot the arrows, and I'm going to plot them at 0, 0, and I'm going to plot them for each layer, but at the same z. So, and then I need the u component, u, and then the v component of the velocity. I think like that works. And then I'm going to do a pause so we can see what the code is doing. And I guess I'll fprintf hit any key to continue. Fprintf. Like that. Let's try it. Okay, clear all, close all, ek. I didn't define row 0. I did not. Row 0 is equal to 125, and this is density kilograms per meter cubed. Clear all ek. Didn't I just define row 0? Oh, nope. Row 0. Clear all ek. Z, I guess I never defined z. I have zs and zv. So zv. Clear all, close all. The size of x must match. So size of zv, size of u. Okay, so the z's are defined as rows and the u's and v's are defined as columns. So MATLAB is finicky about that. So maybe I can go back up here and redefine this to be a column. So zv is equal to zs colon. Oh no, I'm going to just make this one over here. Zs is equal to zs. Make it into a column. So this convert zs from a row vector to a column vector. And if I do that, then zv will then be a column and everything else will follow, I think. Oops. Clear all. Alright, so this is at the beginning, we just turn on the wind. That's the second time step, third, fourth, fifth. This doesn't look right. But it's hard to know because it's so coarse, but I think it's wrong. But let me see. Let's add more points and have a better look at it. There's n is equal to, let's pick 90 points. Clear all, CLF, EK. Let's see, what am I doing wrong? No, that's right, yeah, row by row 0. Divide by row 0. That way this divergence of momentum, if I divide by row, I'll get the velocity, or the divergence of the momentum flux per unit volume, divided by the density, I'll get back the velocity tendency. Alright, let's try it again. Clear all, EK. Let's see what we get. So I have my finger on the return here, and we can see the arrow is spiraling. Right at first, the current was purely in the zonal direction, in the direction of tau x, and then as time goes on, the arrows are getting both longer. I don't know if you can see, but the axis here, this is the U, this is in meters per second in the x direction, and this is in meters per second in the y direction. This one is negative, this one's positive. The arrows are getting both longer because the scale is rescaling, and the arrows, the shorter ones, are the deeper down arrows, velocities as they're being spun up. Okay, so that seems to work. I don't know if it's exactly correct, but what we will do, whoops, is take out this pause, quiver, do a draw now, and then run it again. Let's run it for more days. Let's run it for 10 days. 10 days, maybe I can make this 60 seconds again. I don't know if it'll blow up. Clear all, close all, decay. No, it's blowing up. So one thing about this numerical scheme here, where I just update by multiplying by dt, if I make dt too big, then the discrete, the solution of the discretized time derivative can become what's called unstable, and there will be some spurious computational mode because we didn't take the limit of delta t going to 0. That will cause the solution to grow exponentially. And so we have to make sure that our delta t is small enough. So I try to be too aggressive, and I made it 60. I'm going to back off a little bit and just pick 10 seconds. Clear all, decay, let's try again. And we can sit back and watch the Ekman spiral spin up. I guess something that would be nice would be to, first of all, make the axes bigger, label them, and maybe have a counter showing the time somewhere. So we're going to do that now. Let me stop it, Control C. Alright, so X label is U in meters per second. The Y label is V in meters per second. And then I'm going to have a print out what the time is. So title, maybe T title is equal to S print F. T equals percent 4.2 F backslash N. T divided by 24 times 60 times 60. So this will be the time in days. I guess I should put it in days. Like that. And then title is TTL. And set GCA font size 16 so we can see. And then draw now. And I guess I'm going to do this. I don't need to do every single time point because it kind of evolves slowly. So I'll do this every, let's say every 10 time steps. Or maybe every 6 time steps, every minute. Yeah. So let me add a counter here. K equals 0. K equals K plus 1. And then if mod K 6 equals 0. In other words, if k is a multiple of 6, make the plot, otherwise don't bother. So we're just going to plot every 6 time step so that the thing goes a little bit faster, because MATLAB is a bit slow to make the plots compared to do the calculations. And we're doing this real time. Clear all, dk. Alright, so there's the current is spinning up. And the spiral is developing. I guess one last thing we should do is compare this solution to the exact solution which we've already coded up before. But the exact solution, all we have is the final one, the one at steady state. So you notice that as time goes on, the arrows are changing less and less. So that's as we're approaching the final steady state. the rate of change of the arrows is becoming weaker and weaker. But the arrows are only always getting stronger as the current. See, the top arrow is changing, but very slowly. And then as we develop the layer deeper and deeper down, we're spiraling in. We add a grid. Maybe we can do this less often. So what is my time step size? Is 10? Let's pick it. Yeah, that's okay. Maybe we can do every 60 multiples of 10. That's every 600 seconds. Maybe 36. So 360. So that would be every hour. Add a grid. Grid on. Right. Let me stop it again. Control C. Clear all. Close all. OK. That's 10 days already, so let me go longer. T is 10 days, let's pick 20 days. Clear all. Okay. It's a little bit annoying that the size of the axes keeps jumping around. I guess I could set the size of the axes right at the beginning to avoid having it wobble around like that. So maybe it's not quite in steady state. Maybe I can go up to 30 days, 1 full month. 30 days. And then I will also try to plot, set the axes, the width, before here, axis, and what is the size here? It's from minus 0.02 all the way up to 0.06. And the y is minus 0.07 all the way up to 0.01, like that. That way it won't keep resizing the axes at every time it plots. And then I would like to plot the analytical solution, so let's see if I can bring it back up from what we coded before. Ekman.m over here. Maybe just out here I will define the analytical solution. And let me plot the analytical one. Quiver, 0 star ZV, 0 star ZV. What did I call it? I lost track what I call it. U Ekman A at ZV, U Ekman of V Ekman A at ZV. And we're going to plot these ones in red, like that. And then we're going to do a hold on. I guess here I would CLF. I don't know if that will erase the plot and we won't see anything. Oh, hold off on me. Hold off, yeah. So that the next time I can replot the red one and the blue one again. Oh, I should give this one a color. Blue. Alright, let's try it. Clear all, close all, EK. Oh, wait a minute. I didn't check. Yeah, that looks right. A mistake. Tau x. This should be tau x wind. So this only works, this analytical solution only works for the case where the wind is totally in the x direction. I don't have the solution analytically for the case where I have a component both x and y, whereas the numerical code will work equally well for wind stresses in both directions. But we're just going to use the analytical to make sure the numerical code is working correctly. Clear all, EK. So we're getting the things spinning up, and it's looking pretty good. It looks like it's going to match quite well. The numerical and the analytical solutions are becoming closer and closer as we spin up to the steady state. And so it looks like we did a good job at the analytical solution and a good job at the numerical solution. So, pat on the back. I think this stops at 30 days. It looks like it's pretty much spun up. Yeah. Alright, so I'll post the code on the class website and you can play around with it if you like. So this is a first, I guess, example of solving a partial differential equation using finite differences on a computer. Alright, see you.